Part A. Bernoulli's equation for a fluid flow can be written as P plus half dV squared plus HdG equals constant, where all symbols have their usual meanings, so that the term half dV squared has the unit of energy per unit volume. We can consider the given term half dV squared. Half dV squared. We can write half density is mass divided by volume, V squared. Then we know that half mv squared is the kinetic energy. We can get unit of half mv squared as joules divided by unit of volume, cubic meters. Then unit is joules per cubic meter. Part B. Sri Lanka has one of most advanced ancient irrigation system in the world, such as irrigation system which supplies water for farmers and villages consists of three major features as shown in the figure. Feature 1, the tank or reservoir and the dam. Feature 2, the outgoing water channel from the tank which is exposed to atmosphere. Feature 3, the Pesuru, also known as cistern fluid. It is a rectangular shaped vertical tower chamber with walls made of stones or bricks, seen in figure 1. When it is required to release water from tank, the water is first allowed to enter the Pesuru, in which speed of water flow is drastically reduced. One reason for the reduction is the sudden increase in the cross-sectional area of water flow within the Pesuru. In addition, a substantial amount of energy of water flow is also lost within the Pesuru due to the collision of water with the stone walls of Pesuru. For your calculation, assume that steady and streamlined flow conditions can be applied along the dotted line path shown in the figure, and the height of the water level in tank remains unchanged. Consider the irrigation system, which consists only the features 1 and 2 as shown in figure 2. Part 1. If the height of water level in the tank is h, derive an expression for the speed v1, the outgoing water at point q in terms of h and g. We have to consider the figure 2. It is like this. There is a dotted line like this. This point is S and this point is Q. We have to find the velocity at Q. It is marked as V1. This height is H. It is not changing with time because of there is a large cross-sectional area for the tank. Then we can use Bernoulli's principle between S and Q. I will write by using Bernoulli's equation between S and Q. S is this point, Q is this point. We know that pressure at this point is atmospheric pressure. I will consider P0 plus velocity at this point is 0. Therefore, half rho v squared. We can write p plus half rho v squared plus h rho g at point S equals to p plus half rho v squared plus h rho g at point Q. Pressure at point S P naught, it is at atmospheric pressure. Half rho v square term is 0. Then h rho g, they have given density as d, h dg equals to pressure at this point also P naught because of it is open to the atmosphere. Velocity v1, therefore we can get half d v1 square. H rho g value is 0 because of we can consider this level as the potential energy 0 level, this level. Now we can cancel out P naught and P naught. Then we can cancel out D and D. We can subject V1 to H G root. It is answer for B part 1. Now part 2. If H 12.8, calculate the value V1. Then we can substitute. V1 equals to H value 12.8 G10 root. 128 into 2, 256. Root 256, 16 meters per second. Part 3. Calculate the kinetic energy per unit volume carried by the water at point Q. The density of water is given as 1000 kilograms per cubic meter. Then we can get kinetic energy per unit volume is half B part 3, half dv squared. Now velocity is v1 for the point Q. Half density 1000 v squared 16 squared 256 divide by 2 128,000 joules per cubic meter. Again part C. To control the destructive power of the outgoing water, ancient engineers incorporated the feature 3, the Pesuru tool, to the tank as shown in figure 1. Part 1. The water enters from the tank to Pesuru through the tunnel as shown in figure 1. Assuming that tunnel is tapered and areas of cross-section of tunnel and inlet and outlet are A and 0.6 respectively. Calculate the speed Vb of the water flows at point B in the tunnel. Take the speed of water flows at inlet E of the tunnel is as 12 meters per second. There is a tunnel like this in the first figure. Point E is this one, point B is this one. Now we can use continuity equation. We know that A1 V1 equals A2 V2. Area at E, A. Velocity is 12, it is given in the question. Area at B, 0.6A. We have to find velocity. I will consider it as V2. We can cancel out A term, 12 divided by 0.6. 120 divided by 6. V2 is 12 divided by 6 to 20 meters per second. This is the velocity at this space. They have given it as Vb. Then I will use Vb for the velocity. Then part 2. Calculate the pressure Pb of the water flow at point B in the tunnel. The atmospheric pressure is given as 1 into 10 to the power 5. We can apply Bernoulli's equation between S and B. T plus half dv squared, half rho v squared plus h rho g at point S should be equals to P plus half rho v squared plus h rho g at point B. Pressure at point S is the atmospheric pressure. It is given as 1 into 10 to the power 5. It is open to the atmosphere. You can identify point S. 1 into 10 to the power 5 plus half rho v squared term. It is found as velocity at S 0. Therefore, this term is 0. H rho g. H value is given as 12.8. Then we can get 12.8 density of water 1000 G10. It should be equals to PB, pressure at B, plus velocity at B20. Then we can substitute half density of water 1000, velocity 20 squared. This H rho g term is 0 because of B is at energy, potential energy 0 level. Now we can find PB value. 10 to the power 5 plus 1.28 into 10 to the power 5. This is 1 into 10 to the power 5. We can cancel out 2 and I will substitute it. PB plus half into 1000 into 20 squared 400. Divide by 2, 1, 200. 2 into 10 to the power 5, we can bring it to the left hand side. 1 plus 1.2, 2.2, 1.28, 2.28. We have to subtract 2. Then 0.28 into 10 to the power 5. It is the pressure at B. We can write it 2.8 into 10 to the power 4 Pascal or Newton per square meter. Then part 3, consider a point C in the outgoing water canal where the pressure and speed of the water flows at value 75% of PB and 65% of VB respectively. Write down the values of pressure at water flow PC at point C. They have given it directly. We can write part 3. PC should be equals to 75% of this pressure. 75% of 2.8 into 10 to the power 4. We can cancel out 10 to the power 2. No, I will cancel out it with 75. Divide by 25 4. Divide by 25 3. 7. 0.7. Then 2.5 1 into 10 to the power 4 Pascal. It is the pressure at point C. 3 part 1. Then part 2. Write down the value of speed of water Vc at point C. Then calculating velocity. They have given that velocity at C is 65% of this velocity. 65% of 20. Divide by 25. 13 meters per second. Then part 4. Calculate the speed V2 of outgoing water at point D. You can identify point D by using figure 1. Now we have to use Bernoulli's equation between point C and D. Bernoulli's equation between point C and D. P plus half rho V squared plus H rho G at point C equals to P plus half rho V squared plus H rho G at point D. Pressure at point C we have found in previous calculation 2.1 into 10 to the power 4. plus half density 1000, velocity at point C found as 13 square. This value is 0 because of it is in the lower level. We have considered potential energy 0 level as the lowest level of the diagram. Equals to pressure at point D, it is open to the atmosphere, 10 to the power 5, plus half density 1000, velocity squared, Vd, you have to find Vd value, velocity at point D. H rho g is again 0. Now we have to simplify it. Divide by 2, 1, 500, 2.1 into 10 to the power 4, plus 13 into 13, 169 into 500, minus 10 to the power 5 equals half into 1000 Vd squared. We can write this one with 10 to the power 5 value, 0.21 into 10 to the power 5, plus 5 into 9, 45, 4 remaining, 5 into 6, 30 plus 4, 34, 3 remaining, 5 into 1, 5 plus 3, 8. We can write it 0.845 into 10 to the power 5 minus 10 to the power 5. 500 Vd square. We can add these two terms and subtract this one. 10, 0 plus 5, 5, 1 plus 4, 5, 2 plus 8, 10, 1 remaining, 1, then subtracting 1, we can get 0.055 into 10 to the power 5, divide by 500, foot. It is the Vd value. You can simplify it and get the value 3.32 meters per second. Vd. Part 5. Calculate the percentage loss in the kinetic energy per unit volume carried by water at point D, shown in figure 1, respect to the value calculated in part 3. We have calculated in part B3 kinetic energy per unit volume. It was found as 1.28 into 10 to the power 5. Now we have to calculate kinetic energy per unit volume at point D. Then I will calculate kinetic energy per unit volume at point D. Half d Vd square. Half density of water 1000. Vd square means square of this term. 3.32 square. I will use it 3.32 square. Then we can simplify it. Divide by 2, 1. Divide by 2, 500. 500 into, you know that 3 squared 9, then 3.232 squared, 11.02. We can get it as 11. 2 zeros, 55. 5,500 joules per cubic meter. Now we can find the percentage loss of kinetic energy. Kinetic energy loss divided by initial kinetic energy. Multiply by 100%. Kinetic energy loss. Kinetic energy calculated in part B3. 1.28 into 10 to the power 5. We have to subtract this value. Initial value 1.28 into 10 to the power 5. And we have to multiply by 100% to get the percentage. Then you can simplify it and you will obtain 96%. Part 6. Explain briefly how ancient engineers managed to control the destructive power of outgoing water flow by adding Pesuru to the irrigation system. We can write by destoving a significant amount of energy. Answer for part 6, by destoving a significant amount of energy of the water flow within the Pesuru.